So that was the story about how to get a completely natural electroweak symmetry breaking potential. And as I mentioned, it's very nice that the electroweak symmetry breaking potential is completely natural, but of course the problematic aspect is that it's completely natural at the price of having the Hicks somewhat heavy. Yes, and we know that unfortunately, at least for those models, yes, the Hicks is not 3400 GeV. Yes, so that part that seemed to be a very big gain back in the early 2000s is actually, not a positive aspect of the model anymore. So the way I would like to start out today is to talk about another version of these composite Hicks models, the one that is called the minimal composite Hicks model. So this is called MCH, or minimal composite Hicks. And again, I would like to at least give you the most important features that are distinguishing this model from the ones that we have talked about before, and also explain, why this is called minimal. And in order to fully be able to do calculations in this model, we will have to wait until the end of the lecture tomorrow, where we are going to embed this into a warped extra-dimensional theory, and that will actually give you, all the features of this model. But at least, some of the structure and some of the important aspects can be discussed relatively nicely and easily in the four-dimensional context also. So the main motivation for looking at this minimal composite Hicks model, at least initially, is our electroweak precision observables. As I mentioned, what we did in, for example, the litless Hicks is we introduced top partners and spin 1 partners, and those usually have to lie at around the scale of 1 TeV. Yes, because those are the particles that are cutting off the quadratic divergences. They are necessarily not lying at 10 TeV, but at somewhere 1 TeV in order for us to have that hierarchy stabilized. Yes, but those will start introducing themselves corrections to electroweak precision observables. Yes, as I mentioned, 10 TeV is completely safe for electroweak precision. 1 TeV is not necessarily safe. Yes, if you get 1 TeV suppressed corrections to electroweak precision observables, you could get in conflict with lab data. Okay, so I will not talk in detail about what actually these electroweak precision observables are. So that's something that could be a possibly nice exercise for the discussion session with Javi later today. I just mentioned that there are objects that are called the S and the T parameter. And it turns out that the strongest constraint is from the T parameter. However, it turns out that there are relatively simple ways to make sure that these corrections to the T parameter are not going to be very large. And they are, in the context of little Hicks or composite Hicks models, actually there have been 2 possible ways that people were considering reducing the corrections to electroweak precision observables. One of them went under the name of T parity. So that was sort of, an analog of, so this would be a Z2 symmetry. And so this was invented as an analog of the Z2 symmetry that people are using in supersymmetry called R parity, where people have made all the superpartners odd under a new symmetry, which under a discrete symmetry, yes, which is called R parity in the case of supersymmetry, and that made sure, for example, that all the superpartners are going to be produced in pairs, that the lightest superpartner is actually stable. Yes, so that was a really nice feature of supersymmetric theories, and the people who were thinking about this, they also realized that, this kind of symmetry has an additional important ingredient, yes, which is to make sure that actually, all the electroweak precision corrections due to the new particles, if there is a parity under which all the new particles beyond the standard model are odd, is also going to impose that all the electroweak precision observables are actually generated at most at the loop level, that there will be no tree-level effect to the electroweak precision corrections. So no tree-level effect. So the T-odd particles, yes, will only contribute to electroweak precision observables at loop level. Okay, so no tree-level effects. Okay. And again, it's pretty easy to understand, yes, because when you're looking at, for example, at any process that was measured at lab, yes, you are only having standard model particles on the external legs, yes, and if you have a tree-level exchange of some of the heavy particles, yes, that would be forbidden by this T parity, yes. You would have to have at least two of them, yes, but they cannot be in an external, particle, so there's got to be a loop. Yes, so the effect of this was to say that, well, even if the particle is at 1 TeV, yes, you would say you could worry that from a tree-level effect there is some effect that is suppressed by 1 over the top partner mass, for example, that is at 1 TeV, but because there's an additional loop factor, yes, or 1 over mt squared, yes, there would be an additional 16 pi squared loop factor showing up there. So effectively, the suppression scale is not going to be the mass of these particles, yes, but it's going to be 4 pi times the mass, for example, of the top partners or the spin 1 partners, and that's perfect, yes, because if this is 1 TeV, then the suppression is going to be pushed to 10 TeV, and that's roughly the region where the electroweak precision bounds are already going to be safe, even if you just write down generic stuff. Okay, so that was one of the directions. Yes? As I said, I will not explain that. That's a whole lecture on its own. Yes, Javi maybe in the discussion section, but basically, you should just think of it for now as higher dimensional operators, dimension 6 operators, yes, made out of the standard model fields, and they are suppressed by some scale, yes, and so they are operators, yes, and then their coefficients, yes, out of those you can make some parameters, yes. Okay, so yes. Right, there could be, yes, so that wouldn't be a problem, yes. The problem is, some of these models, it's very hard to really make every particle truly be T-odd, yes. So that, for example, if you try to put, you have a triplet like we had yesterday, yes, top, bottom, and then a third guy there, yes, there's at least one guy that better be T-even, yes. So it's not completely trivial to make a simple model, yes, where all the so you really have to complicate the model in order to make sure that all the new particles are T parity odd. So I think that's the biggest problem of those, that some of these models are already complicated, and then to make sure that you have T parity is getting, really, Anyway, so I just wanted to mention this as a possible direction. This is, I will not talk about, there's a whole set of models that are called, little Hicks models with T parity. I think it's a good idea for you to understand, what the new ingredient here is, yes, if you go and read those papers for some reason, but I will not try to go into the detail. The one that I would like to talk about is this minimal composite Hicks model, and there the approach is somewhat different. So the approach there is that I will not forbid all the corrections to electroweak precision observables. I will only be focusing at least to leading order to the one for the t parameter, and for that one there is actually a symmetry that can forbid large corrections to the t parameter. Okay, so to forbid just the t parameter, there's something called the custodial symmetry. Okay, and again, what I will do here is to explain what custodial symmetry is, and I'm hoping that Javi, in the afternoon will discuss for you how, custodial symmetry actually really protects the mass ratio between the W and the Z, and then the object that is called, sometimes it's called the rho parameter, sometimes it's called the t parameter. Okay, it's the same thing roughly. Okay, so the nice thing about this object again is that there's a symmetry that can make sure that those corrections are vanishing, while for the other one, for the that is mainly constrained, it's not as bad as the t parameter, but it's also sometimes strong constraint. There is no symmetry for that one. Okay, so the custodial symmetry is a symmetry of the standard model, an additional global symmetry of the standard model that is an accidental global symmetry. Okay, so of the standard model Hicks sector, and it's an approximate symmetry, so it's not an exact symmetry. And the easiest to understand what the symmetry is to just, go back to the standard model Higgs potential and try to, for example, as the most pedestrian way is to just say, let me write it out in terms of the real components of the Higgs doublet. Yes. I can take the Higgs doublet and write it as H1 plus IH2, H3 plus IH4. Yes, so this is my Higgs doublet. Yes, and I roll it out in terms of real and imaginary parts. Yes, and now let me ask the question. So what is, what are these invariants that are showing up in the Higgs potential? Yes, well, the way I can write it is, I'll take the absolute value squared. Yes, that's going to be H1 squared plus H2 squared plus H3 squared plus H4 squared. Yeah, so this is minus mu squared times H1 squared plus H2 squared plus H3 squared plus H4 squared. Yes, and if I write the H to the 4, yes, that's going to be the square of this combination. Yes, so what you see is that actually, these terms that are showing up in the Higgs potential, they have a bigger symmetry than just SU2. Yes, in fact, yes, so you can see that if I write it just as a 4-component real field, yes, it will have a full SO4 global symmetry. Yes. So it will have a full SO4 global symmetry, and you probably all know, yes, that the SO4 global symmetry is bigger than an SU2 global symmetry. In fact, it is actually equivalent to 2 copies of an SU2 symmetry. Yes, so those of you who know a little bit of group theory probably have seen this. SO4 is equal, at least locally, to SU2 left cross SU2 right. Those who think they don't know it probably also know it, yes, because this is roughly the Lorentz group if you take it, with different signatures, yes, and you know that in the Lorentz group, yes, you have 3 rotations and 3 boosts. Yes, that's roughly the same structure that is underlying the Lorentz group. Yes, so from that point of view, you have seen this even if you didn't realize it. All right, and then of course, the identification is that this is the gauged SU2 left, yes, of the standard model. And then there's this additional piece, this SU2 right symmetry, yes. So that's sometimes what is called the custodial symmetry, this SU2 right symmetry. Or another way to say it is that the symmetry breaking pattern of the standard model is that you have this SO4, and that one is broken down to an SO3, yes, because if I think of the Higgs web in terms of this H1, H2, H3, H4, four-component vector of SO4, yes, one of these is going to get vacuum expectation value, so the SO4 is broken to SO3, yes. Now, SO3 is equal to SU2, yes, so that everybody knows, yes. And this now, of course, is not equal to SU2 left. We know that this web does break the gauged SU2 symmetry, yes. So this is now a global SU2, and sometimes this is the thing that is called custodial symmetry. So that notation is a little bit confusing. Sometimes people call the additional SU2 right that is showing up before the symmetry breaking the custodial symmetry. Sometimes people are calling the remaining one after the Higgs gets the web, the remaining SU2, the custodial symmetry. Doesn't matter, you know. As long as you roughly understand the real picture under it, doesn't matter which one you call the custodial SU2, yes. But again, the upshot is that there is a bigger symmetry, yes, and that symmetry is what is actually going to ensure that you get the right mass ratio between the W and the Z boson. So for example, I mentioned at the very beginning of these lectures that QCD also breaks the Electroweak symmetry, and it turned out that, you know, we wrote down the nonlinear sigma model. Yes, we found what the mass from QCD is to the W and the Z, and I said, look, it looks miraculous that actually, you know, the expression for the W and the Z mass coming from the chiral condensate in QCD looks exactly like the one from the Higgs boson in the standard model, even though the sources are totally different. Yes, one of them, you know, has no scalar, is just dynamics, yes, and the other one here, yes, is, you know, is coming from a scalar field, yet the expression for the W and the Z mass is exactly the same. Well, this symmetry is the one that ensured that, yes, because there the symmetry breaking pattern was exactly the same. Yes, we had the SU2 left cross SU2 right, chiral symmetry of QCD. Yes, so those were the subgroups of the SU3 left and the SU3 right, and they were broken to the diagonal. Yes, SU2 custodial, that's the same thing. SU2 left cross SU2 right, broken to the diagonal. That's exactly what is happening in the standard model also. Okay, so that was the reason, if you remember back then, about the story of Technicolor giving you the right ratio of W to Z masses. Okay. Now, of course, you know, one more thing, just that, of course, this is not an exact symmetry of the standard model, yes, this custodial symmetry. For example, you know, hypercharge is partly a subgroup of SU2 right, yes. Gauging a subgroup of a global symmetry, as we discussed previously, is an explicit breaking, yes. So turning on hypercharge, that's one source for breaking custodial symmetry on the standard model. And then actually turning on the Yukawa couplings, that's a second source for breaking the custodial symmetry. Okay, so custodial symmetry is an approximate symmetry. So it's not an exact symmetry, meaning that, you know, a part of the standard model, namely the Higgs sector and the SU2 left gauge interactions, they leave it as an exact symmetry, and then U1 hypercharge and the Yukawa couplings break it. Okay, so actually within the standard model already, you know, there are sources for breaking this custodial symmetry, but, you know, those are things that you can go ahead and calculate and find, you know, what those so-called corrections to the T parameter or rho parameter are. And, you know, you will see that, you know, for example, the top Yukawa coupling will give you the largest contribution, and then hypercharge, etc. Yes? Right. So another way to think about, what this SU2 left and SU2 right is in the doublet language is to say that actually this is a consequence of the fact that actually the representations of SU2 are what is called pseudo-real, meaning that if I take the complex conjugate of the Hicks doublet, yes, okay, so that's like, I take a representation with the lower index. If I take a complex conjugate, for example, for SU3, yes, a fundamental and an anti-fundamental are two totally different representations. But in SU2, it's a different story, yes. Actually, the representation for the complex conjugate of the Hicks is equivalent to the fundamental, to the original doublet of the SU2. Okay, so one way to think about this is to say that so if I say that the Hicks has, one lower index as a doublet of SU2, yes, then the complex conjugate would have an upper index, and now I can actually lower it back with the with the 2 by 2 epsilon tensor, and now this is also fundamental. So this field and the original Hicks transform exactly the same way. Okay, so this field is sometimes called H tilde. Okay, and then what you can do is you can put the H and the H tilde as a 2 by 2. I'm sorry? Well, again, so this is just a complex conjugate, yes? Well, again, this is SU2 here, yes? So this is acting, this is not a fermion here, yes? So this is not quite, it's just saying that, that SU2, is a pseudo-real representation, yes? So again, the point is that H and H tilde, yes, you can arrange them as a 2 by 2 matrix, yes? And now you have exactly the story that you were interested in. From the left, yes, both of them transform with SU2 left, yes? But then when you mix up these two, the H and the H tilde, yes, that is now going to be a global symmetry, yes? That's the SU2 right. Okay, so that's another way of understanding, how in this language, in the language of the doublets, yes, is the one that is gauged, is the normal.
Yes, but it transforms only one part or both of them.
Well, it transforms, both, it's the same thing, so it better transforms both of them, yes. Right, that's what it means that, this is a 2 by 2 matrix and it transforms from the left by the SU2 left transformation, yes? So both of these, so this is, this is a column vector and there's another column vector. So from the left, both of these transformed in the same SU2 left. And then when you mix the two together, H with H tilde, yes, that's the new thing. That's the SU2 right. Okay. So that's how to discuss it in the language of the doublets, yes? Or, in this language, of course, again, it's really simple. The only thing that is not so simple then is now. So where exactly is the SU2 left? Yes. So that's the way to translate it back and forth. All right, very good. So that's the story of the custodial symmetry. And again, this is really useful to protect, the whatever beyond the standard model you have against the largest and most dangerous corrections to electroweak precision observables. So what this minimal composite Hicks model does for you is to explicitly incorporate custodial symmetry into the global symmetry breaking pattern and make sure that such corrections will be absent. Okay, so the main feature of these minimal composite Hicks models is that custodial symmetry is explicitly maintained, incorporated, and maintained. Okay? So again, this is basically a motivation for taking a particular global symmetry breaking structure, yes? And the pattern that we are going to take here is that the original global symmetry is SO5, and that one is broken down to H, yes, which is going to be SO4, yes? So SO4 is sort of the symmetry of the standard model, including the custodial symmetry, yes? So in this symmetry breaking pattern, the custodial symmetry is left explicitly unbroken and it's explicitly incorporated, yes? So this pattern will make sure that there will be no corrections to the electroweak precision observables beyond what you're already getting within the standard model, okay? So that's why this is useful. And why is it called minimal? Well, now you can start counting what the number of Goldstone bosons is. Yes, so the number of generators for SO5, yes?
But we said before that custodial symmetry is broken
By hypercharge and Yukawa couplings, yes? So it will be broken here also, yes? That's, of course, okay, yes? And in fact, you want that, because those corrections are something that are needed in order for you to get agreement with the electroweak precision observables. What is nice in this model is that there is no source for custodial symmetry breaking beyond the standard model. So the physics beyond the standard model doesn't break the custodial symmetry, yes? If putting the Yukawa couplings and hypercharge will be there here also, yes? And it has to be part of the whole structure, but the BSM part does not break the custodial symmetry.
And those corrections from custodial symmetry in standard model, they're checked on experiment.
Right. So those are very well checked, absolutely, yes.
And what is the result? We just don't see the symmetry, or we prove that, does it exist, or how is it?
Sorry, the
Custodial symmetry.
well, again, the result is that the measurements of, so the way these electroweak precision observables are tested is by, measuring lots of parameters, at the z-pole in the lab experiment, okay? And the result is that, all of those observables are consistent with having custodial symmetry only broken by hypercharge and the Yukawa couplings. Well, again, if you don't introduce it generically, if you don't have it in the BSM sector, yes, generically, the BSM sector will give you additional contributions to the electroweak precision observables. And of course, there's a possibility that they, for some miraculous reason, cancel, yes, or become very small, yes. But generically, the answer is, if you don't have custodial symmetry, if the BSM physics comes at 3 level, it will usually be immediately excluded. Okay, that's the generic story.
This custodial symmetry is a kind of, you said like T parity, it conserves.
So T parity is again, it's a different approach. Yes, so there you do not necessarily have custodial symmetry, but you make sure that all the corrections come at one loop. Yes, while here, there could be, corrections to electroweak precision observables at 3 level, just not to the T parameter. Okay? That's roughly the story. Any other questions? Yes? Right. Right. Absolutely. Yep. Right. Right. So it's quadratically sensitive to the corrections of the top mass and logarithmically sensitive to the corrections of the Higgs mass. So that's why there was a this program in the early 90s to predict the mass of the top. All right, so let me go and give you the structure of this minimal composite Higgs model. Again, so this has 10 generators. Yes, SO4 has 6 generators. Yes, so the number of Goldstone bosons is 4. Yes. What are those 4 Goldstone bosons? Well, it's very easy. Yes. You start out with an adjoint of SO5. Yes, which is, what is it? It's an antisymmetric of SO5. Yes. So you end up with an antisymmetric of SO4. So the broken generators are going to be here, yes, and they will form exactly a 4 of SO4. Yes, so the broken generators are going to be here. So you can write this as your pion matrix H1, H2, H3, H4, at least in the SO4 language. Yes, these are going to be all real, and it's an antisymmetric matrix. Yes, and that is going to be your pion matrix. Yes, so why is it minimal? Because it gives you exactly one Higgs doublet worth of Goldstone bosons, nothing beyond that. Yes, so it's minimal because there is a single H doublet that is going to come out as a Goldstone boson. Yes, and it has, you know, this whole custodial symmetry built into the theory. Now, from here, we can sort of start turning the crank. Yes, we know, for example, how to write the gauge interactions of these Hickses using our method for, you know, generating the nonlinearly realized field. Yes, so we can write our field. I'm going to call it sigma here, e to the I pi over f times sigma 0. Yes, so this is again, you know, the same story as we started out with QCD, and then we did it for the simplest little Higgs, etc. Yes, so you can go ahead and explicitly do this. Yes, so the sigma 0 is going to be 0, 0, 0, 0 f. Yes, so this is the VAV that is breaking SO5 down to SO4. Yes, so it's a 5 of SO5. That is the one that is giving you the right breaking pattern for breaking SO5 down to SO4. And then this exponential here is, well, you just have to go ahead and exponentiate this field, you know, making sure that it's properly antisymmetrized. And you can go and just explicitly calculate what this is. So I'm gonna tell you what this is. I'm not going to try to go through the calculation. H over F over H. H1, H2, H3, H4, and then H times cot H over F. Okay, so this is what you get when you are trying to expand this whole nonlinear sigma model field. It's actually not even an expansion. This is the exact result. Yes, you can just exponentiate it and use usual trigonometric relations, where little h is the absolute value squared of the doublet, yes, under the square root, which is, you know, h1 squared plus h2 squared plus h3 squared plus h4 squared. Okay, and then the capital H, the doublet notation going back and forth between the two, is just h1 minus I h2 and h3 minus I h4. Okay, so you can go back and forth between them. And this is the full nonlinear field, yes, the exact expression for it. And now you can, you know, start asking the question, what are the interactions with the gauge fields? Yes, well, we know the recipe again is the same story. Yes, I know where the I know where the standard model is embedded in here. Yes, because the standard model is embedded into the SU2 left subgroup of the unbroken SO4. Yes, and then hypercharge is embedded into T3 right. Yes, so we know exactly how to do this calculation. Again, I'm not going to try to do it because I would mess it up and I would bore you, and so there are many reasons for that. Yes, but again, you just take this field, yes, put in the covariant derivatives with respect to the standard model fields, and calculate what the resulting interaction Lagrangian is. Okay, so let's do that explicitly. Let me write the result down. Okay. Yes, always. Pi, yes. Well, so again, so this is again in a so this is in the SO4 language. Yeah. So this here is the unbroken SO4, and then this is well, so the whole thing is SO5. Yes. So there's one column here and one row here. Yes. And the adjoint of SO groups is an antisymmetric matrix. Okay. So here you have exactly, so here you will have minus H1, minus H2, minus H3, minus H4. Yes, so that they are not independent fields. Yes, it's exactly the same field that has to show up here and over here, and then of course here there's a 0. Yes. Okay. Very good. So yes, you take that pi matrix, you exponentiate it, you get the expression of the actual field, and then you get your kinetic term as we did before, and that is going to give you the interaction with the standard model gauge bosons. And what you're going to find is interaction with the standard model gauge bosons 1/8 f squared sine squared h over f times there's b mu plus whatever the usual story w mu 3 minus 2 w mu 3 b mu plus 2 w mu plus w minus times, you have to make sure that the indices are properly contracted, doesn't matter. Eta mu nu minus q squared. Okay, so the important thing is that another important concept that I would like to introduce here is that the fact that you have these nonlinearly realized fields is going to always introduce some amount of deviations of the interactions between the Hicks and the standard model gauge bosons compared to the standard model predictions. I think this is somebody was asking a few days ago, yes, what is the consequence of compositeness, of the fact that the Higgs is a composite and it's not an elementary one, yes? How will I see that in experiments, yes? Well, actually, this is a nice place to see it, yes, because from these interactions, what you will find is, take this field and expand it in terms of the VAV and the fluctuations around it. Yes, so right now H as the VAV of H plus some fluctuations. Yes, I'm going to take it H tilde. Yes, and what you will find is that actually, the expressions that you are getting, for example, for the interactions between the W's and the Higgs, is not quite exactly the same as what you're getting in the standard model. There will be small corrections to that. Okay, so the first thing is that this prefactor that you are finding here, yes, this f squared sine squared h over f, once the h gets the VAV, this whole thing is what has to be identified with the VAV of the standard model Higgs. Yes, so one thing that is important, yes, is yes. Yeah, probably new.
It's some strange combination, like H is not independent field of H1, H2, and H3, H4, right?
H again is the sum of all of them. Yes.
But
the square root of h1 squared plus h2 squared plus, yes.
But do we have enough dynamics for those 1, 2, 3, 4?
Well, again, of course, after Electroweak symmetry breaking, yes, some of them are going to be, as usual, the Eaton Goldstone bosons, which provide the longitudinal components of the W and the Z, and then one is going to be the physical Higgs. So when I do this expansion here, yes, I will assume that there's only one remaining physical degree of freedom, yes, and I go to the gauge where the additional 3 guys are just becoming Goldstone boson, and I just set them to 0. Okay, so that's the trick I'm doing here. Okay. So again, but what I want to emphasize is that the first point is that this expression here, as once I shove in the VAV for H, is what is supposed to be the mass of the W and the Z, yes, with the right combinations. Yes, so actually that combination is what is supposed to be identified with sine squared H VAV over F. Yes, this is what should be identified with the 246 GV in the standard model. Yes, so because you have this trigonometric function showing up here, yes, the H VAV is not quite the same thing. Yes, what the VAV in the standard model is. Yes, so this is the right identification. How to go between this actual VAV, yes, and the observed 246 GeV number that is coming out from the mass of the W and the Z. And then what you can see is that because it's actually this trigonometric function that is showing up in front, yes, when you are starting to expand the H around its expectation value, yes, and identify the fluctuation around the expectation value with the Hicks, yes, this, expanding the sign is not quite the same thing as expanding here the function with, that would just be an H squared in the standard model. So you will start picking up small corrections, yes, at the point. So when I just shove in the H, that's of course just the definition of what the VAV is, so that you can completely absorb, yes, in this definition. But once you made this choice, yes, to match the mass of the W and the Z, at that point, when you are going to look for the interactions of the Higgs with the W and the Z, there will be small corrections showing up. Yes, so it's actually pretty simple. Yes, all you have to do is literally, expand this function around its VAV, and just pick out, what the corrections will look like. So these corrections are usually parameterized in terms of this parameter that is called psi, which is v squared over f squared, yes, which is nothing else but literally the sine h over f, sine squared h over f, yes. And so you can go ahead and do this, and what you will find is that the corrections will look like, so this term here, yes, rather than just going as h, what you will find is that the corrections will go as, if you expand this term, v squared plus 2v1 minus psi h plus 1 minus 2 psi h squared plus higher order terms. Yes, so that will tell you that the couplings to the standard model gauge bosons, yes, for example, the couplings of 2 gauge bosons with a single Higgs, so that's the one that, LHC is starting to test at higher and higher precision, yes, is going to be given by the expression for the standard model, yes, times this root 1 minus psi. Okay, and then of course there will be deviations for double Higgs couplings also. Yes, so there will be additional corrections like that. 1 minus 2 psi. Yes. So the upshot is that it's this V over F, that is the parameter that is telling you how much deviation you are expecting in ordinary Higgs physics. And these particular numbers, yes, how you are, what this particular coefficient is, that's somewhat model dependent. Yes? So that does depend on the group theory structure. Yes? So the particular numerical values for the coefficients of psi depends on the group theory. Yes? But the generic structure that you are expecting shifts by, this V over F squared suppression, yes, that's general in all of these models. Okay, so that's one of the most concrete ways to think about testing these composite Higgs models. Yes. Right. So in this particular model, these are the results. But if I took not SO5, but for example SO6, these coefficients, whether this is a 2 here or, you can get other numbers here. Okay? But you will always get these shifts that are proportional to psi. Yes? Well, so we'll come to that, how the SO5 mod SO4, what the Higgs potential is. I'll show that in a moment. Okay, but again, this the second lesson to take away from today is to say that, well, generically in composite Higgs models, you do expect the properties of the Higgs to deviate slightly from the standard model Higgs properties. Yes, and the parameter that is telling you about the amount of deviation is this ratio here. Yes, and this ratio is very important. Yes, because it is roughly telling you how heavy the top partners and the gauge boson partners are. Yes, so we know from experiments that this psi cannot be super large. Yes, because well, the LHC is starting to measure the couplings of the Higgs now to order 10% level. Yes, so the expectation is that this is something less than 0.1. Okay, so that means that V over F is, something of the order of 3 or 4 at most. Yes. Yeah, you can call, yeah. Right. I think that's generic. Is that right, Javi? That it's always less than 1. But in bigger groups, do you remember what the answer was? Always less than 1. Yes. Right. I mean, it will take a while to, to be sure, yes? That it is there no way to correct it, to make it bigger than 1? I don't remember. Do we know any model? Do you remember? Where's? Okay. Right. Right. So anyway, so this is a really nice way to try to test these models. Of course, as I said, the precision is not, I mean, it is getting better and better, but it's something of the order of 10% right now. So V over F, you would say is less than, a third or a fourth or something like that. So that's still not, sort of mortally dangerous because, I mean, if V is 246, yes, F is a TV, that's still roughly okay, yes. So, will you get things like, W times 3 gauge bosons? Yes, you will get couplings like that, yes. Right, yes, yeah. But of course, we haven't even seen the double couplings, yes. So measuring something with 3 Hickses in the final state is even, is gonna take a long time. All right, very good. So now somebody was asking me about the structure of the Higgs potential. Yes, well, there's one more really important story to discuss here, namely the fact that because this minimal composite Higgs is minimal in the sense that there are no additional Goldstone bosons generated here, yes, there is no room here for a 3-level quartic, yes. So MCH, yes, has no additional Goldstone bosons. And we saw yesterday that the way you can possibly get an order 1 3-level quartic, yes, was through, messing around with additional Goldstone bosons. Some are collective, some are not collective. Well, there are no additional Goldstone bosons here. Yes, so here the quartic will be loop induced. Okay. It cannot be as large as it is in the littlest Higgs model, yes, where, through this weird, having, the triplet, and then there were these 2 additional terms and the cubic interaction, we got this term that eventually looked like a collective quartic, but it was large. Yes. Here, there are no additional Goldstones. It cannot be large. Yes. It cannot be 3-level. Yes. So it will be also induced at the loop order. Okay. So the structure of the Higgs potential, the expected structure of the Higgs potential will be, well, there will be a quadratic term, just like for the case of the little Higgs models induced at the loop level, minus 1 over 16 pi squared. Then there's a standard model coupling here, yes, and then it's cut off by the top partners, yes, the quadratic divergence. So I can write this as G star squared F squared. Yes, so that will be the roughly the magnitude, just like in the case yesterday for the littlest Higgs, yes. But then the story for the quartic will be different, yes, because yesterday for the littlest Higgs, the quartic was given by just the G standard model squared. Here there's an additional loop suppression. Here you will get G standard model squared times G star squared over 16 pi squared. Okay, so again, the difference between the minimal composite Higgs and the standard model Higgs is that there's in the little Higgs models, this is 3-level and is reasonably large. Here there's an additional loop suppression for the quartic. Okay, so there's one thing that this is nice. Yes, I was complaining to you yesterday that the little Higgs models are predicting a too large Higgs mass. Yes, well, that's not a problem here. Yes, because now the quartic is loop suppressed. Yes, so the quartic itself seems to be roughly the right magnitude. Okay, so that's sort of, you can take it as a plus. Now the problem is that now if you start minimizing this potential, yes, you can see that, well, roughly the prefactors for the quadratic and the quartic term are the same, and the only sort of remaining dimensionful parameter is the scale f. Yes. So now, because I have this additional loop suppression here, the Hicks wave is not showing up at f over 4 pi, right, like it did for the little Hicks models, yes, but the Hicks wave naturally wants to show up at the scale f. Yes. So, say it in another way, it would like, if I just take this structure for the Higgs potential, it would want to get V over F is equal to 1. That would be the natural location of the minimum of these type of Higgs potentials. Yes? So this is in the minimal composite Higgs. Of course, in the little Higgs, what I had is V over F was 1 over 4 pi. Yes? So that was what I called completely natural electroweak symmetry breaking, but it required a relatively heavy Higgs. Now I don't have a relatively heavy Higgs, but now the Higgs potential is not completely natural, yes? Because I know that, well, V over F better be less than V over F squared, better be less than 0.1, yes? Now I will have a tuning of order V squared over F squared tuning in the Higgs potential. Okay. So that's something that you basically just have to live with, at least in these models. Yes, so the idea is that, okay, well, the way to make this happen is to actually, have an additional contribution here. Yes, so for example, from the gauge sector, try to play these two against each other, yes, and then reduce the size of this term, yes, compared to how large it would naturally want to be, yes. So it's a little bit of the tuning, of the same tuning that we were trying to fight is actually already showing up here, yes. And now the source for that is to actually get the right Higgs wave. Okay. Yes. So collective symmetry breaking is included here, yes. So that collective symmetry breaking made sure that this is, not that this number here is not lambda, but it's so this here is, for example, MT. So this is the top partner mass. That's where I already assumed the collective symmetry breaking, yes. Otherwise, I would have put here lambda, the cutoff scale, yes, and then it would have been even much worse. Yes. So then it would have pushed it up all the way to, yeah. So collective symmetry breaking is already included here, and yet you need a little more additional cancellation just because you don't have, the right size of the quartic. Yes. But the problem is, if you had the right size of the quartic, then the Higgs mass would be heavier. Yes. So that's. Sorry, which one? Yeah, so this is 246. Yes, right. So this is the amount of tuning that is there in these, minimal composite Higgs type models. Okay. Now, at this point, I will deviate. I will leave the minimal composite Higgs model. Of course, there are some things I haven't told you. Yes, I haven't told you what are the spin 1 partners, what are the top partners. How to introduce those. Those are of course needed for getting the collective breaking. Yes. Here it was just assumed that I have it. Yes. And I'm going to leave it because the way we are going to introduce those is via the extra dimensional particular construction for the minimal composite Higgs models. It looks like there's a very simple extra dimensional version of these models, and again, the aim is to try to get there by the end of the last lecture tomorrow. So again, I will leave this a little bit aside, but before I move on to extra dimensions, there is one more topic that I would like to start discussing, and that's the story of the fermion masses partial compositeness, and the flavor structure of these models. So I'm going to talk about fermion masses, and in particular, I will talk about the story that is called partial compositeness. And I will also like to explain, the general flavor structure of these models, and people may have heard these names: anarchic flavor models, RS Jim mechanism, etc. And fermion masses. Okay, very good. So the story is that, of course, in strongly coupled theories, there are several ways of being able to get fermion masses. So originally, in technicolor models, the initial attempt at getting fermion masses was to write down 4 Fermi operators. And those 4 Fermi operators would include, 2 of the fermions that are actually eventually getting a condensate, and then when 2 of those fields condense, then you are going to get, some fermion mass. Okay, so just very roughly, you would write, operators of this sort, psi, psi, and then the technicolor fields, and then when these fields condensed, yes, then you obtain the fermion mass. Okay, so it's a nice idea, but it had many, many problems associated with it. In particular, it was very, very difficult to get rid of flavor-changing neutral currents. In fact, even before, the Hicks was discovered, or even before electroweak precision tests were making, technicolor models somewhat implausible, just the fact that, this flavor structure looked so horrendous, yes, that, cast a big shadow of doubt on technicolor models. Now, it turns out that there's another way to go in generic strongly coupled theories, and that's the story of partial compositeness. So the other direction, which is other than having these 4 Fermi operators, is to say that actually the source of fermion masses could be due to the mixing is from a mixing of the standard model fermions with some heavy composite fermionic objects. Okay, so the story here is to sort of assume that for now, for example, that the standard model fermions are just introduced externally and they are not part of the strong dynamics. Okay. And this will have a very nice geometric picture in terms of the warped extra-dimensional theories tomorrow. Was there a question somewhere? Yes. 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 Right. Yes. Right. Right. So okay. So you get something like sine squared h over f something like 1. Yes. Right. Again, I mean, generically, just the fact that you have a sign here is not going to really help you with. I'm sorry? Right. Again, if you look at the particular models, and they are always going to give you a tuning of this amount, okay, and it's very hard to get around that. I mean, there are attempts, of getting around that. I was playing with that. For example, you can maybe try to get another source for a 3-level quartic that is, not as large as the one, but if you just look at these theories, that tuning, that is what is called an irreducible tuning nowadays. So that one is very hard to get rid of. In fact, it turns out that there's usually even more than this. Okay, and then once there's more than this, then you start worrying, okay, this was 10%. I started trying to solve a 1% tuning, and I'm getting back a theory with 1% tuning. Anyway, fermion masses. So the story here with this partial compositeness is to assume that the fermions, the standard model fermions, are external to the strong interactions. And what I mean by external is that, that they are not bound states of the composite sector. Yes, they are just, just introduced by hand. Yes, they are just elementary fields. Yes. And again, there is no necessarily a problem. Yes, fermions don't have hierarchy problems, etc. The problem is, of course, somehow they will have to start feeling the effect of the Hicks, yes, which is a composite field. Yes, so somehow you have to be able to mediate, these elementary fermions that are introduced, like in the standard model, and they are massless to begin with. Yes, you have to somehow generate an effective Yukawa coupling for them. Yes, through the composite sector. Yes, and the story is that there's a really nice way to do this is if you are just mixing these elementary fermions with some of the composite fields of the composite sector, and the assumption you make about the composite sector is that it has a bunch of massive fermions among their composites. Yes, so there's no massless field, no massless fermion in the composite sector, but there's a tower of all of these heavy fields there, and the standard model fermions end up mixing with some of those composite fermions. So this is the story of partial compositeness. Okay, so again, the way we are imagining it is that we have our standard model fields, let's say psi left and psi right, and then there will be some mixing between the elementary fields and some operators, some fermionic operators in the composite sector. Lambda right, psi bar right, O left. Okay. So these are the standard model fields. They are the elementary fermions. And these operators, these are some composite fermions. And they are the ones that, whose spectrum is going to include, some towers of massive fermionic fields. Okay? So let me imagine, let me give you a simple heuristic picture that I think, explains exactly everything that is happening in this partial compositeness story. So let me assume that these O left and O right operators, their lowest excitations are described by the fields phi left and phi right. Okay, so these are their lowest excitations. And I will just give you a simple Lagrangian that is, ordinary, fermionic Lagrangian mixing, just the standard model fields with these fermionic massive fields that are arising from the composite sector. Okay. So let's try to get that story straight. And how will I do this? So I will have a lambda left here, and then the characteristic scale that is going to descend from the composite sector is the scale f. So all of these mixings are going to be proportional to the scale f from the composite sector, and then I will have here my operator psi left bar phi left. Yes, I will have a similar term for the right-handed sector, lambda right f psi right bar phi right. Okay. And then, of course, these fields are supposed to be very massive. Yeah? So they are supposed to have their own mass terms with, so let's say this is a left-handed field, yes. Then there should be a complex conjugate field corresponding to that, yes, with which this guy is actually forming mass, a very heavy massive state, yes. So then there will be a plus m left times phi left, and then I call this other guy phi left bar. Yeah, so this is the field. This is another composite fermion. Yeah, so this is a two-component fermion, and this is the corresponding composite two-component fermion with which these fields are going to get their heavy mass. Yes, and then plus m right times phi right bar. Okay. I'm sorry. This. Yeah, so again, the assumption is that I have some heavy composite fermions, and this is just saying that this is a heavy composite fermion, yes? So this is the mass that, the compositeness produced for these fermionic fields, yeah? So this is a heavy composite fermion, and that's what its mass is. And in addition, I'm adding this mixing between the standard model field and the heavy composite fermion. So these are all two-component fermions, yes? Okay, but of course, in the composite sector, you have to have both the left and the right in order for those to be heavy composite fermions. So that's what this term is representing. That's the same thing for the other guy that my right-handed fields are mixing with. And then these are the elementary fields that I added in by hand, which have a small mixing with my composite fermions. Okay, and there is one more piece that is important here. Yes, of course, there's got to be a Yukawa interaction somewhere, yes, an interaction with my composite Hicks. Now, where should I put it? Yes, well, the Hicks is composite, so it shouldn't be interacting with the elementary fields, but it can have a Yukawa term among the heavy composites. Yes, so there will be an additional term of the form y times phi left bar, phi right bar times h. Okay, plus Hermitian conjugate. Everything is plus Hermitian conjugate. Okay, so again, this is the mixing. This is the composite fermion masses. Yes, and then this is the Yukawa, but it only acts in the composite sector. Bar means it's another field. Yes, it's really, truly another field, yes? It's, let's say if this is a left-handed field, then this would be a right-handed field, or, the complex conjugate, or a left-handed in the opposite representation of the gauge group, yes? So these are two different fields here, okay?
And also, we are looking for psi L. It's a doublet or?
So these are standard model fermions, yes? Are they doublets or singlets? It depends on, am I talking about the left-handed guy or the right-handed guy, yes? So they have exactly the quantum numbers as the standard model fermions. Some of them are doublets, some of them are singlets, yes? I mean, okay, so, well, let's say these are doublets and these are singlets, yes? Okay, so, okay, is the picture until here clear?
But if we have already a mass term for composite fermions, why do we introduce the color?
So we don't, okay, so this will be a small perturbation for the masses of the heavy fermions, yes? So they are not very important in terms of shifting the masses of the heavy fermions, yes? But the claim is that this will be the origin of the Yukawa terms for the remaining, for the emerging light fermion, which will be a mixture of the elementary and the composite fields. Okay, without this, yes, clearly, there's no Hicks, there will be no Yukawa term, yes? The only place where it can show up is in an interaction among the composites, because this is composite and these guys are composite, yes? But somehow the claim is that there will be a descending small residual Yukawa interaction for these fields, which are not going to be exactly these fields, but they are going to include a small mixing with the heavy guys. Okay, so that's the story that I'm trying to say. Not for the fermions, yes, because those are elementary. At least in this simplified picture, they are elementary, the others are composite. The composites feel the Higgs, the elementary, they don't, yes. But, somehow you are allowing this mixing. So the key is for you to be able to have this mixing between the... okay, very good. So now what am I supposed to do? Yes, well, now I'm supposed to identify what is the remaining light field in this theory. Yes, well, actually what you see is, for example, if you group these two terms together, yes, you can write it as lambda left f plus m left, lambda left. So both of these terms are multiplying phi left, yes, and then you can write it as lambda left f times psi bar left, yes, plus m left times phi bar left. Yes. So what you see is, well, there will still be a massless fermion remaining in the theory, of course. Yes, you know it by chirality. Yes, that's the way I introduce it. When you have a vector-like fermion plus an additional two-component fermion, just by chirality, there will still be a massless fermion present in the theory. Yes, except the massless fermion will not be exactly, the elementary field that I have introduced into the theory, yes, but it will be now a linear combination of the psi bar and this phi bar here, yes. Yes. Right. Right. No, so the assumption is that these are only charged under the standard model. These, fields, they are composites, yes, but they still are charged under the standard model, yes. So, and the one is the complex conjugate of the other. So you can always write a mass term for a Dirac fermion, yes. Okay, does it make sense? Again, it's sort of a simple toy example, but I think, it's really good to understand it, because if you understand this toy example, then you will really understand, the more complicated picture, very easily. Okay. Very good. So again, what you find is, of course, yes, you introduced a Dirac fermion and a two-component fermion. One two-component fermion will still remain massless, yes, but it's not the psi bar left that is exactly massless, but it's going to be the linear combination that is orthogonal, yes, to this object that is going to remain massless, yes. So this object here, this beast, you will identify as the heavy, as a true heavy, field, which is now mainly made out of the composite field. But of course, if this lambda is relatively small, yes, it has a small admixture of the elementary field. Yes. So you can think of this, as a sine and the cosine of a mixing angle. Yes. So the mixing angle would be like sine of, sine left. Yes, would be lambda L f over lambda L f squared plus ml squared. Yes, you can think of this as a sine of a mixing angle and this as a cosine of a mixing angle. Yes, so this will be the true heavy field. And then the important thing is that the light field is an orthogonal combination of these two fields. Is the orthogonal combination. Yes, so it will contain a little admixture of the heavy field also, of the composite field. Yes, so the massless field will have an admixture of the order of lambda LF over ML, yes, times the phi bar left plus, a term, that is roughly order 1. If this term is very small, then roughly order 1, yes, times psi bar left. So this is the light field. Yes, so this ratio here, yes, is what is usually called the fraction of compositeness. Yes, so this is what is usually in these papers denoted as F left, the fraction of the compositeness in the left-handed sector. Yes, and then of course you can do the same game for the right-handed sector. Yes, so you will get an F right there, and you will, of course, same expression, lambda right F over M right. Yes, so the right-handed field will have a small amount of fraction of compositeness in the right-handed sector, which means, yes, that this Yukawa coupling that you have written for the composites, yes, will, because there is a tiny piece of the how much piece, yes, the phi left will contain an F left fraction of the light field. This will contain an F right fraction of the light field. Yes, so what you will get is that the effective Yukawa coupling, yes, the effective Yukawa coupling that is descending from this Yukawa coupling that you have written for the composites, yes, will have the form of F, let's say for the left-handed guys, yes, I'm going to write it now, Q, Y up. This is the formula that is usually written, yes, and then Y down is FQ, Y down, F down, yes. So these Q's are the F lefts, yes, and then this is the F right for the up type field and for the down type field, yes, and these Y's again are the Yukawa couplings that you have written for the up type and the down type fields. Okay, so this is the structure that you're going to get, yes, that the effective Yukawa coupling, yes, that you are observing for your actual light fields, yes, will be proportional to this fundamental Yukawa coupling, yes, that is in the composite sector, yes, times these fractions of compositenesses, yes. So you can play around with these fractions and then be able to possibly explain the fermion mass hierarchies. Okay, so this is again, so this is the basic formula that you see for partial compositeness, and of course, there are really nice stories, and we will try to get to that in the extra-dimensional context for how to make these F's actually naturally exponentially suppressed without really introducing small numbers. So there are nice ways to make the F's exponentially small without just by introducing a proper dynamics. And in the four-dimensional picture, the answer is that you can make some anomalous dimensions very large. And then it's the running from the flavor scale to the scale of compositeness that could give you, these exponentially suppressed F's. In the extra-dimensional picture that we will see tomorrow, those will have interpretations of wave functions in the extra dimension that are naturally going to be exponentially suppressed without, really introducing some small exponential numbers. Okay, very good. So let me just say a few more things about and if you do that, then you get what is called the anarchic theory of flavor. Yes, because by anarchic, what people mean is that actually these fundamental Yukawa couplings could be all order 1. Yes. And all the flavor hierarchy is coming from the fact that you have these very small, admixtures of the elementary fermions and the composites. So this is what people call the anarchic theory of flavor. Anarchic in the sense that you start out with Yukawa couplings that are all random order 1 numbers. There's no structure there. Yes. And the structure will emerge from some additional source. Yes. Which is always, these exponentially small fractions of compositeness. Okay. Now, another really nice exercise for the discussion session could be to take these anarchic or partially composite Yukawa couplings. For example, for the up type quark, yes, you have F, Q, Y up, F up. Assume that these are all order 1 numbers. Yes, and assume that these are numbers that are hierarchical. Yes, so take a 3x3 flavor model. Okay, 3x3 flavor. Yes, so this would be a 3x3 matrix with order 1 numbers, and this would be, the amount of compositeness for the left-handed quarks, and this is for the right-handed up quarks. Yes, and assume that these F's are actually hierarchical. Yes, so there is the first, the second, and the third generation mixings are all, exponentially different from each other, and find out, how, what would be the matrices, what would be the hierarchy of the matrices that are actually diagonalizing this matrix and, fulfilling the usual flavor story in the standard model where you go and, you diagonalize your left-handed quarks, you diagonalize your right-handed quarks, and then, of course, the CKM matrix will be the product of those. Yes. So the usual story is that what you do in the standard model. Yes. You take your Yukawa matrix. Yes. And you have a left-handed rotation. Then you have here a diagonal matrix, and then here you have a right-handed rotation. Yes. And the exercise that you can and hopefully will do is to show that the structure of these diagonalizing matrices, the ones that you are using in flavor physics, is something very special. Yes, that it will also have some particular hierarchies, and they are set by the same hierarchies as it is in these fractional compositenesses. Yes, and the rotation matrices, the left-handed ones, are going to be given by the hierarchies, the minimum of the ratios, FQI over FQJ, or the inverse of that. Okay, FQJ over FQI. Again, this is just simple matrix multiplication. Yes, you assume that there are order 1 numbers here, and then you have numbers that are exponentially different from each other. The question is, when you're trying to do your diagonalization, your singular value decomposition, yes, what will be the hierarchy of these matrices? Again, it's something that it's very easy to see when you actually try to write down those matrices. It looks a little weird, when I write it. But the upshot is that it's going to be given by the ratios of these elements. So for the left-handed guy, it's going to be given by the ratios of the left-handed compositeness. And for the right-handed guys, it's going to be given by the ratios of the right-handed compositenesses. and the value of the diagonal matrix elements, these y up diagonals, will be given by fqi times fui, for example, for the up quark. Yes? So the value of the diagonal matrix elements will be basically given by the diagonal elements of these fractional compositenesses. Yes? And on top of it, you will also know what the order of magnitude of the rotating matrices is. So for the left, it's the ratio of the left-handed compositenesses, and for the right, it's going to be the ratio of the right-handed compositeness. So let's say for up, it will be f up j, f up j. Yeah, so you basically have to pick, whichever, ratio is the smaller one, yes. So you have to, this minimum is just saying, if you order them in the right way, then it's clear which one to take. Okay. And on top of it, what you will find is that then the CKM matrix, yes, which is L up times L down dagger, yes, will also be hierarchical. Okay, so that's again something that is non-trivial, but it's following from going through this exercise, yes, that you actually explicitly generate, what these rotation matrices are, and then you see the rotation matrices are hierarchical, yes, and well, so you have to, the CKM matrices, and the hierarchy in the CKM matrix is only going to be given by the hierarchy in the left-handed part of the quark sector, yes, because it's always the mismatch between the two rotations that you have to do on the left-handed fields. That's what the CKM matrix is, yes, because it's the mismatch in the interaction of the doublets that matters there. Okay, so from that, you are able to basically, get a very nice flavor structure. Okay, so two more comments here about flavor. One is that comment number one, the top quark the top mass should be large, of course, should be reasonably large. And the expression for the mixing between the heavy and the light fields is set by, whatever these ratios are, lambda left right over lambda left right squared plus g star squared for the top quark. Yes, and this is what is telling you how heavy the top mass is. Yes. Now, we were assuming that these mixings are smallish, but okay, at most you can take it order 1. Yes, so that means that the G star for the top shouldn't be extremely large, yes, because if the G star of the top is very large, yes, then this fraction of compositeness for the top will also be very small, and you will not be able to get an order 1 top Yukawa coupling. Yes, so the upshot is that the G star for the top should be order 1, yes, which is good. That's exactly the same thing as we need in order for us to solve the hierarchy problem, yes, which is telling you that the top partners cannot be super heavy. Yes, that's the same. Flavor is also telling you that the top partners should be reasonably light. Yes. If they were super heavy, close to the cutoff scale, yes. 1, they couldn't cut off the quadratic divergence, and 2, the mixing with those super heavy states could not possibly give you, the observed top masses. Okay, so both of these go roughly in the same direction. Yes, so that's that's a good sort of coincidence. Yes, and the second comment is about flavor changing neutral currents. I mentioned to you that there's a big problem with flavor changing neutral currents if I go the other route of trying to generate fermion masses in composite Higgs models. And this one here is actually avoided. Okay, so in partial compositeness, all flavor changing neutral currents are generated through the mixing with the composite sector, yes? Because the assumption is we have the elementary fermions, we just introduce them, as they are. There's no source of flavor changing neutral current in the elementary sector. There could be some in the composite sector, yes? But for my light fields to feel the effect of flavor changing neutral currents, I have to mix them with the composite sector. Okay, so that means that if I have a 4 Fermi operator, yes, for example, the ones that are contributing to KK bar mixing, yes, Q bar Q, Q bar Q, yes, delta F equals 2, yes, it means that for every one of these external fermions that are going to give me a flavor changing neutral current, I will have to introduce, at least one factor of this fractional compositeness. Yes, so I have to introduce, 4 of these factors, yes, and these usually, the ones that are most sensitive are the ones that are for the light quarks, yes. For example, for KK bar mixing, some of them are strange, some of them are up or down, yes. So that means that there is a natural suppression for flavor changing neutral currents built into the structure of partial compositeness. So this is called the RS-Jim mechanism, and hopefully when we get to warped extra dimensions tomorrow, this will become more clear what it is, yes? But the important thing is that there is a natural suppression of flavor changing neutral currents built into this model of partial compositeness. Okay, so that's also very important. Basically, these are proportional. So these factors, again, we know exactly what those factors are in an anarchic theory of flavor, yes, because those will be given by roughly, just Yukawa couplings for the light quarks, yes. So that's really nice, yes. It is telling you that these 4 Fermi operators that you want it to be very small, they are naturally going to be suppressed in addition to the mass scale of, whatever, the compositeness scale is, by a bunch of light Yukawa couplings, yes. And that's turns out to be almost enough to satisfy all the constraints from flavor changing neutral currents. Okay, very good. So this is the story of the 4-dimensional picture, and maybe I will just say a few words about extra dimensions and the non-warped version of the extra dimensions before I let you go for the lunch. Again, the plan is to start talking about warped extra dimensions tomorrow, and then introduce the warped extra dimensional version of the minimal composite Higgs model. So that's the kind of theory that that would be the most realistic one that people are considering, and get to that point. Okay, so for now it looks like a break because you don't really understand why extra dimensions are related to composite Higgs models. But when we introduce the ADS-CFT correspondence tomorrow, hopefully that will become clear. But for now, I'm just going to talk about generic features of extra dimensional theories. Yes, no warping yet today. So again, we are introducing an extra spatial dimension. So for example, a 5D theory. And since we haven't observed the 5th dimension, we are assuming that the 5th dimension is compact, yes, that it's not like all the other dimensions that are infinite, that the 5th dimension is compact. And just for the sake of simplicity, I will assume that it's a circle with radius r. Okay. Now, the most important story about a field theory in an extra dimension is that when you write down the Lagrangian for this higher dimensional theory, from the four-dimensional observer's point of view, from a person's point of view who cannot resolve the size of this fifth dimension, because this size is, for example, very small, this theory will look like an infinite tower of scalar fields, a so-called Kaluza-Klein tower of scalar fields in the four-dimensional theory. Okay, so let's do this explicitly, and I guess that's the last thing I will be able to do today. Yes, so assume that this is a circle. So this extra dimension is compact, and I will also assume that it's periodic. And I'm going to just take a free scalar field, the simplest thing, just for the sake of concreteness, dm phi of x and y, dm phi of x and y. Okay, so m now, of course, is a derivative, is now running over the usual four dimensions plus the fifth dimension. Yes, so m has 5 different values. Yes, and also the phi can depend on both the ordinary 4 dimensions plus y is the coordinate along the extra dimension. Okay, so another way to say it is integral d5x 1/2. I have your usual d mu phi squared here, as minus dy phi squared. Yes. Okay, so you have your ordinary 4-dimensional derivatives and your fifth derivative. Okay, so let me say that the extra dimension is periodic. Yes. Again, it doesn't have to be, but just for simplicity, for now, I'm assuming it's going to be periodic. So in that case, I can write the dependence along the extra dimension in terms of a Fourier series. Yes. So if y is periodic, I can expand the dependence on the fifth coordinate in a Fourier series. Yes. So I can write that there is a phi n of x. Yes. So this would be the Fourier expansion coefficient of the nth Fourier mode. Yes. E to the I n over r times y. Yes. And then I can put here some normalization, and we will discuss the importance of, for now, it's just an arbitrary normalization. Okay. So if phi was a real scalar, then you can make sure that phi n star is equal to phi minus n, and that will make sure that this Fourier series remains real. Okay. Now the important thing is that you take this Fourier expansion, so this goes from minus infinity to plus infinity, into my action. Yes, and how will that action look like? Yes, now S is, I plug it in. Now I have specified what the y dependence of each of these modes is. Yes, so I can just explicitly integrate over the fifth dimension. Yes, so now it's going to be just a 4-dimensional integral. Yes, and it will give me an integral of sum n is positive d mu phi minus n star d mu phi n minus n over r squared times phi n absolute value squared. Actually, I guess I can write it like this. Yes, these two have been identified, so that relation has been used. So you are only summing over the positive values now for n. Yes, and so this is a really important, is a very simple but important formula. Yes, it's telling you that you started out with a 5-dimensional field. Yes, from the 4-dimensional point of view, this 5-dimensional field will appear as a tower of massive fields. Yes? For n equals 0, you get a massless scalar, but for higher values of n, this will actually appear as a tower of massive fields. Okay? And each mass is going to be given by n squared over r squared. Okay, so a 5D field equals a tower of massive 4D fields. Yes, and this is called the Kaluza-Klein tower. And this kind of expansion is called the Kaluza-Klein decomposition of a 5-dimensional field. Obviously, if I had more than one extra dimension, yes, for example, identify on a torus, then I will get similar expressions. Yes, then there will be a tower, an integer that is telling you the amount of winding of this field along the different dimensions. For example, if you just take a toroidal compactification, and then the result will be the effective 4-dimensional mass. Now I can also allowing to put in a higher dimensional mass, yes, plus then there will be n5 squared over r5 squared plus n6 squared over r6 squared plus etc. So that would be the generalization for the case when you have more complicated extra dimensions. Still assume that it's all periodic. So for example, in a torus, and that's that would be how a Kaluza-Klein decomposition would go. Okay. Very good. So I'm going to stop here, and in the next lecture I will very briefly explain what happens when you're doing the same thing for gauge fields, and then we'll talk about matching of couplings, how to introduce branes, and hopefully we'll move on to warping and then ADS-CFT correspondence quickly.